So when we want to graph equilibrium, we're typically going to look at the rate of reaction and how that's going to change over time. However, we could also look at the concentration of each individual species for the reaction and identify how that is going to change over time. And so when we graph the rate of reaction, we want to graph both the rate of the forward reaction and the rate of the reverse reaction so we can understand what's happening to both. So an example of that is this here, where we can see that the rate of the forward reaction is decreasing and the rate of the reverse reaction is decreasing. And then when it reaches this plateau here at what we've called time t1, they've attained equilibrium because the rate of the forward reaction is now equal to the rate of the reverse reaction. So we can do an example with this here, where we consider the effect of changing the pressure of the system and how that's going to affect our equilibrium graph. So we can see that the forward reaction and the reverse reaction are initially starting off at equilibrium, but then what we're doing is we're going to decrease the volume of the container that the gas is in. And so by decreasing the volume, that is compressing it down and increasing the pressure. And so with this system, we can see that we've got N2 plus 3H2 makes 2NH3. So we can see on the reactant side of the reaction, we've got 4 moles of gas, whereas on the product side of the reaction, we've only got 2 moles of gas. So remember we said before that if we are to increase the pressure of the system, we've decreased the size that the gases can occupy, so they want to produce the least moles of gas. So they're going to want to favour the production of the products, so hence they'll be favouring the forward reaction. So we can see that if we're to graph that, initially, when that volume is first decreased, we see an increase in the concentration and an increase in the reaction rate of both the forward and the reverse reaction. However, we then see that the change in equilibrium is re-established, and we can re-establish our equilibrium again by the lines plateauing in order to re-establish that equal rate of the forward and the reverse reaction. And so we can look at this here in terms of the concentrations, and we can see that our concentrations of all of the reactants and the products have increased in accordance with their molar ratios. So when we had that increase in pressure, because we decreased the size of the container, so decreasing the size of the container was going to increase the concentrations of all of them. But then we can see that it is followed by a decrease in our reactants, so N2 and H2, and then an increase in our product being the NH3, and that's because we're favouring the forward reaction and not favouring the reverse reaction. So now we can look at what would happen if we were to decrease pressure, and so we can see that we would have the reverse of this, because decreasing pressure would be increasing the size of the container, so we want to favour the side of the reaction with the most moles of gas, and so that's going to be our reactant side of the equation, which we remember had 4 moles of gas as opposed to the products which had 2. And so far we've been considering changes to the system that cause rapid changes in the concentration, and so that's always going to show as that vertical spike in the concentration or time graphs. But when we consider temperature, that's not going to be the case, and so that's how you can tell when you look at one of these graphs what effect has actually been applied. And so all of the effects we've actually looked at so far will have no effect on the equilibrium constant, so that being our concentration or our pressure, but temperature will have an effect on our equilibrium constant. And so we'll have to look at the equilibrium constant in a little bit so that we can understand that in relation to temperature. So when we consider temperature, we can consider this same example here. And so the direction of the shift for the reaction when we change the temperature in an equilibrium reaction is going to depend on whether the reaction is exothermic or endothermic. So with this reaction here, we need to consider if our forward reaction is exothermic or endothermic. And so what we can see with this reaction is that we've been given a delta H value. And this delta H value is negative 92 kilojoules per mole. And so because we can see that our delta H value is a negative, that means that there is heat being lost in the reaction. And so we can consider if heat is being lost in the reaction, it is being given off as a product. So you'd say that this is an exothermic reaction. Conversely, if this was positive, it would mean that it's an endothermic reaction because it would mean that heat is being consumed by the reaction. So if the forward reaction is exothermic, increasing the temperature will decrease the equilibrium constant. And this is because it is driving the reaction to the reverse in order to absorb the heat. Whilst decreasing the temperature is going to increase the equilibrium constant because the equilibrium will shift to the right. And so if the forward reaction is endothermic, increasing the temperature is going to increase the equilibrium constant, and decreasing the temperature is going to lower the equilibrium constant. And so this is because basically, if we're considering an exothermic reaction, we're considering heat to be like a product. So if we were to be decreasing the temperature, it would be like taking heat out of the system. So it would be like taking product out of the system. And so if we're taking product out of the system, we want to favor the forward direction of the reaction in order to replace the heat that is being lost from the system. And if we were to increase the temperature, we'd be putting heat into the system. So we'd want to favor the reverse reaction in order to then counteract the effect and use up that excess heat which is being put into the reaction. Then if we were to consider an endothermic reaction, that would be where heat is being absorbed. We would consider that heat is like a reactant. So if we have heat as a reactant, increasing the temperature would be like putting heat into the system. And so we want to use up that excess heat which has been put into the system. And so we do that by favoring the rate of the forward reaction because we want to use up the excess reactant which is being put in. Whereas if we were to decrease the temperature of the endothermic reaction, it would be like taking heat out of the system. And so it would be like taking reactant out of the system. And so we want to favor the reverse reaction in order to counteract that effect. So when we consider looking at this on a graph, we can see that if this was our graph with our forward reaction and our reverse reaction, we can see that when the reaction mixture is heated, we have a change in which we have an increase in the reverse reaction and a decrease in the forward reaction. And if we're to look at this in terms of a concentration time graph, we can see that because it is an exothermic reaction, we can see that if we're to cool the system, so be taking heat out of the system, we're going to produce more products because it's an exothermic reaction, so heat is like a product. And then we're going to produce less of the reactants because reactants will be used up in order to make the products. So finally, we want to consider how catalysts will affect the graph. So we can recall that catalysts, they're not going to affect the position of equilibrium. So when we're graphing these, we would see that when adding a catalyst, the beginning of the reaction will just be reached faster. So we will just attain the equilibrium faster, not actually affect the position of equilibrium. And if the reaction was already at equilibrium, adding a catalyst would have absolutely no effect at all on the position of equilibrium, because it would be increasing the rate of the forward reaction and the rate of the reverse reaction at the exact same amount.